So in today's lab, we are going to dynamics of the ethyl benzene problem, which we have done in the last lab. So you have a converged flow sheet from the previous lab. So open that converged flow sheet and do the following. So from the starting, you have to just you go to the column and for each column go to the analysis and report and open the include hydraulic parameters. We need a hydraulic parameter for each column to calculate the diameter and length of the reflex and sump level. Uh, Sump level. So for each column, first open the analysis report and include hydraulic parameter. And then the simulation. After running the simulation, you have seen that in profile tab there is a hydraulic tab is open, and you have the data for vapor and liquid flow, mass flow, and mole flow, and their densities also for every stage. Then after that we need a diameter of the each column. So for diameter, go to the sizing and rating and tray sizing, and here we will use from second number 2 to last number tray, that is 10th, because 11 tray is revolver tray and first tray is your condenser tray. So we go from second number tray to 10 number tray, because there are total 11 trays in C1 column, and we will use the sieve tray here, sieve trays, and this will be done for each column. Now in the second column we have total of 24 trays, so we will go from 2 to 23, and then trays and sieve, we will use sieve tray in each column. And the third column we have total of 29 trays, 2 to 28, and tray type is sieve. We run this. After running, we will go to the result of the sizing and rating, and in the result we can see diameter of the column. Okay, now after getting the diameter of the each column, we will need diameter of the reflux drum and diameter of the sump level for each column, and as well as diameter for the CSTR, both CSTR also. So we have to calculate this. So to calculate the diameter, we have to go to profile section and go to the hydraulic, and we have to calculate the volumetric flow rate for condenser and revolver or sump in cubic meter per minute. So this is the volumetric flow rate for first tray, because the liquid in the first flow will go to the condenser. So this volumetric flow rate will go to the reflux drum. That's why we will use this reflux drum in the this tray volumetric flow rate for reflux drum, and the second last tray for sump level. Now we will calculate the diameter, and the diameter will be, and we will use the 10-minute folder for each reflux and sump level. So for reflux of C1 column 4518 multiplied by 10 minutes, we will get the volume of the reflux drum. So from the volume we have to we have to find the diameter of the reflux drum. So to find the diameter, we use the length is equal to 2 times the diameter. So pi d square by 4 into L is equal to volume. So where L is equal to 2, so we will get diameter is equal to 2V by pi ki power 1 by 3. So we will multiply by 2 here and divide by pi to power 1 by 3. So we will get the diameter of the reflex drum approximately 2.29. So for C1 column, diameter of condenser is 0.29. We will 0.3. We have to find the sump and then diameter of the column. So for sump, volumetric flow rate is 0.58. So 0.581806 multiplied by 20 divided by pi to the power 1 by 3, 1.54. We will use 1.55, and diameter we will get from the sizing and rating result. C1 column diameter should be 0.65. So diameter is 0.65. For C2 column, similarly we have to find all these data for C2 column also. So same concept will be applied here. Volumetric flow rate 0.279432 multiplied by 20 divided by pi to the power 1 by 3, 1.21 condenser, and sump is volumetric flow rate liquid 0.44, 0.449347 multiplied by 20 divided by pi to the power 1 by 3, which is 1.42. And then we need diameter. So diameter is upon 1.1. 1.1. Then we will then C3 column condenser, sump, diameter. C3 column condenser, hydraulics, volumetric cubic per minute 0.708027 multiplied by 20 divided by pi to the power 1 by 3, 1.65, 1.65 and 0.893659 power 20 divided by pi to the power 1 by 3, 1.7879. Diameter 1.67. Okay. After okay. So for CSTR, for CSTR we have to calculate the volume for the CSTR. Since the volume of the CSTR we have given, that is 200 meter cube, and we will use the length is 2 times of diameter. So for that the volume is 200 meter cube and pi d square by 4 into L, where L is 2d, so pi d cube by 2. So multiplied by 2 divided by pi की power 1 by 3. So this is the volume diameter for the CSTR 5.03. Since the volume for both the CSTR is similar, 200 meter cube, so for both CSTR the diameter will be the 5.03. So after getting all these all the data for the level and column diameter, so we have to just go to the dynamic port, dynamic tab, and click the dynamic mode. So after clicking the dynamic mode, you can see all the column and CSTR are red in color from left hand side. So from first one by one we will give the data to each column. So in C1 dynamics, reflex term should be your vertical, and head type is your flat, and diameter I have calculated is 0.3. So diameter is 0.3, so length should be 0.6. For sump level, for sump, head type is your flat, and diameter for sump is 1.55, and height is 3.1. Here we have to give the total number of stages from 1 to second last, and second last stage is 10 number tray, and diameter is dia is 0.65, and we don't need to give the spacing, wear height, L by D ratio, percentage active area for opportunity. These all datas Aspen take by default. If we need to change this data, we will change it according to our need, but in this for this lab we don't want to change this data. So for we next this is completed, C1 column is completed. Now we will go to the C2 column. In C2 column we will give the same task we will done here, and for C2 column the diameter of the condenser is 1.21, 2.42, sump for sump is 1.42, 2.84, and height for hydraulic C2 called C2 24 trays 2 to 23, and diameter for the diameter is 1.1. Now for C3 column, diameter is 1.652, 3.304. For sump, dia is 1.79, 3.58, and total trays is 29, 2 to 28, and dia is 1.67. For CSTR, dia is 5.03. For CSTR2, dia is 5.03. Now all the dynamic data are completed. Now run the simulation. After running the simulation, all these tab will be active. After all these tab active, first we have to check the pressure checker. We have to run the pressure checker. What pressure checker will do is it check the pressure of each line and each unit operation, and see the pressure of the column, the pressure of the unit operation, and the pressure of the stream will be same or not. If it is not same, then it will show you some error, and if it is same, then it will be run. So here it says for C1, C2, C3 column, the feed stage pressure is not same. So we have to check what are the pressure for the each stage, and we have to give the same pressure for the inlet stream. So for go to the for C1 column, go to the profile and see what was the pressure of the inlet stream. Since stream is in for feed stage is fifth stage, and the pressure of the fifth stage is 8.04. So we have to give the pressure at the outlet, is 8.04. Okay. Now for the similarly for the C2 column, for C2 column feed stage is your 8 and pressure is 1.17. 1.17, wall is B13, so outlet pressure is 1.17. Now for the C3 column, feed stage is your sixth stage and the pressure is 1.15. So B14, pressure is 1.15. Now run the simulation. After run the simulation, just check once again pressure is similar or not. Yes, flow sheet is configured to be fully pressure driven. Now then we have to just pressure driven, click on the pressure driven to export the steady state file to pressure driven in the dynamic environment. I will add one more folder here. New folder, EV Dynamics, and save here. I will save this EV Dynamics here. It will give some warnings. So let's not waste our time in here. Now our dynamic files are open. Before going to the dynamic, I want to show you one more thing. In each column, when I will go to the dynamic port, there is a one more tab is controller tab. So in controller tab, what it will show is it will automatically add some controller in the dynamic file. So which are the controller do you want? You should check here, and accordingly it will be controlled from that. So in C1 column, it says pressure of the top section will be controlled by vent vapor flow rate. So I don't want to control the pressure from the vent vapor flow rate. I want pressure to be controlled from the condenser duty. So I will reselect pressure will be controlled from the condenser duty, not vent vapor flow rate. And reflex drum level will be controlled by reflex flow rate, and sub level control will be controlled by the bottom rate. These all correct. Bottom stage temperature will be controlled by the reboiler duty, but I need some lag here, so I will not select bottom stage temperature. For C1 column, I want this control structure, and for C2 column, I want pressure to be controlled by condenser duty. Reflex drum level will be controlled by the liquid distillate. Temperature of the top stage I don't want to control. Some level controller, everything is fine. I want top 3 temperature for C1 column also, but it is not. So okay, in C3 column I want pressure to be controlled by condenser duty, reflex from everything is fine. Now again go to the run the simulation, pressure checker and pressure driven. In pressure driven, EV Dynamics, save here. After save, you have to wait for some time to open that dynamics file. Now your dynamic file is open, and you have automatically some controller are automatically given, and your all the pressure of the column is controlled by the your condenser duty. Okay, now we will want to control the, now we will do apply all the control structure in the flow sheet. Okay, for control structure, just for controller, just click on the PID in the bottom and put it here, here, here. I want this sump level here, distillate rate, reflux drum, sump. This is your fresh benzene flow controller or total benzene flow controller. For as you know, the best control structure here to control the benzene is you have to take the total benzene that is given, go to the CSTR and control by the fresh flow rate. So I will use total benzene here, and it is this PV for the controller, and the output of the controller is your valve position. Okay, now this controller is your fresh ethylene flow controller, and we will use here fresh ethylene. Okay, now CSTR level, first CSTR level controlled by the respective output flow rate, valve position. This controller is your CSTR LC. Okay, this controller is C2 drum level, drum LC. This controller is your C2 sump LC. This controller is your C3 drum LC, and this controller is your C3 sump LC. Okay, now connect all these controller. Now here is stage 1 level. We have to select stage 1 level for drum level, PV and OP. Now output is your valve position. Here stage 1 level, PV, OP, valve position. Now here is your sump level at the bottom, sump level, OP wall position, sump level PV OP wall position. Now how many controller we have right now? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, and we have total degree of freedom of 5 5 5 15 15 4 19 19 21. We have 21 degree of freedom, and we have right now 9 13 15 controller. So we need 6 more controller. So 6 more controller will be all the column controller. So here this wall is left, so we need in the C1 controller, in the C1 column, we want the drum temperature to be 50 degrees centigrade. So how to ensure drum temperature 50 degrees centigrade is to leak the excess benzene. So we will use here stage 1 temperature, and we will control the stage 1 temperature by controlling the wall of the vapor rate. So here is C1 top TC, and C1 top TC, so it is stage 1 temperature or condenser temperature, and it will be controlled by this wall position. Now second thing is your temperature revolver duty. So to control the revolver duty, the work of revolver is to remove the more volatile component from the bottom. So which temperature we have to use? We will go to the steady state, and from the steady state we will make the composition temperature profile for the column. And as you can see, these two trays, actually from the tray number 6 to tray number 10, we can see it is a separation of binary system, because the composition of the DEB will be is constant for tray number 6 to 10. The only thing changes will be the benzene flow rate and the ethyl benzene flow rate. So it is a binary separation from 6 to 10. So we will use a tray which have sharp change in temperature. So we can see at stage number 6 the temperature difference is maximum. So we will use the stage 6 to control the temperature of this C1 column. So or duty of the C1 column. So for here there is a one controller, and we have to put the lag also, and lag time is your 1 minute as given in the problem statement. So here is your temperature of the sixth stage temperature. Controlled by revolver duty. This is your C1 TC. Now in the second column we have 2 degree of freedom, that is one is revolver duty and other is your reflux rate. So for reflux rate I will use the L by F ratio. So for L by F ratio I will use the multiplier, and in the multiplier the input goes from the S16 mass flow rate, because in here we have only mass flow rate, reflux mass flow rate, so we will give the mass flow rate and we will use the reflux mass flow rate. This is your L by F of second column. Control F, L by F of second column. Okay. Now the value of L by F. So for that we have to go to the steady state and then go to the C2 column and see the feed mass flow rate of feed. So feed is S16 and total mass flow rate in kg per hour. I want kg per hour. Mass flow in kg per hour. So total mass flow rate of the feed is 15,668.4 and reflux rate is 15,668.4 and reflux rate is kg per hour 10,387. So 10,387.9 divided by 15,068.4. Value is 0.662984. 0.662984. Input 2 is fixed, which is value of L by F. So we have input 1 is your fresh feed rate. So fresh feed rate multiplied by input 2 will give you the reflux rate. That's how we will use the L by F ratio in the Aspen Plus. And next is your bottom temperature. Now which tray I have to use, we will see from the composition profile from the steady state. C2 TC. Now go to the steady state. C2 column composition profile. Here we have ethyl benzene and DAB. Approximately we can see from the tray number 9 to tray number 22 the separation is between the benzene and ethyl benzene. DAB is constant, so we will see sharp temperature change between tray number 9 and tray number 23. So for that, go to the temperature profile, and from temperature profile we can see the sharp change. There is no sharp change here, but the change in 14 and 15 tray will be the sharp with respect to the last trays. So we will use the tray number 14 here. Now for the last column we will use the L by F ratio and the temperature to revolver. L by F 3 mass flow rate, input 1, and deflux mass flow rate. Now want to see the value. Stream mass flow rate kg per hour S14 12,457.5 12,447.5 and your reflux rate is your 21,485. So 21,485.3 divided by 12,447.5. 447.5. One point 72468. 1.72468. 1.72468. Okay. Now temperature for the last tray, last column. We will use the 28 number tray to control the temperature, or 26 number. Let's see. Composition. Okay. Tray number 24 to tray number 28. There is a sharp change. Tray number 28. So we'll use here tray number 25. We have completed with the control structure. Now we have to initialize all the controller. First, starting from the fresh benzene. So open the faceplate of the fresh benzene, then go to the configure tab. Here first is your auto, second is your manual, then cascade, then percentage, then your configure, then plot, then your tuning. In configure page, now we have to set the action of the controller. Since as soon as your flow rate is increases, you have to close the valve. So this action is reverse action. So this is reverse action, and as given your problem statement, the gain for the flow controller is 0.6 and the tau is your 1, 0.1, 0.5 and 1. Then you have to initialize. After initialization you will get this. So FBFC is your FBFC finished. Then fresh ethylene, fresh reverse action 0.5 and 1, initialize, finish, CSTR TC auto initialized. It will be initialized by the okay. It will be initialized by the Aspen CSTR TC CSTR LC. We have to initialize CSTR LC. So this is the direct action, and CSTR level should be PI, so we will use 5 and 6 and initialize. These are auto initialize 10 and 60, so we will use 10 and 60 here also, CSTR LC also. Or 5 and 6. In CSTR2 we use 5 and 6. CSTR TC, it will be auto initialized. Then C1 condenser pressure, it will be auto initialized. Reverse action. C1 top TC, we have to initialize this. We will use 2 and first time reverse action. C1 dump level will be auto initialized. For dump level, all the levels except for CSTR are P only controller with a gain of 2 and it will direct action. Okay, C1 term, C1 sum similarly 2 and 1 E10. Action is your direct. C1 TC, we will give any value 2. Action should be reverse action. As temperature increases, we have decrease your revolver duty, so action is reverse action. And value, so value we have to calculate it from here. C1 revolver duty in gauge per hour is 2.57336. 2.57336. Put it here. 2.57336. Range is double 5.15. This is C1 TC. C2 condenser pressure, it will be auto initialized. Okay, C2 term level, we have to initialize it with gain of 2 and no integral time with direct action. C2 sump level, similarly 2 1E10 direct action. L by F value is given. C2 TC, we will give some value 2. Reverse action and duty will be given from here. $2.53733. 2.53733. 5.1. L by F3 value is given. C2 converter auto initialize. C3 drum level 2 1E10 direct action. C3 sump level 2 1E10 direct action. C3TC, some random value, reverse action, initialize, value given from the Aspen, steady state, gigajoule per hour, 10.5925, 10.5925, 21.18. All the controllers are open. Put it on same place. Now one more thing, your fresh benzene will be in ratio with the fresh ethylene. So we will give ratio controller, rotate, this is your ratio, ratio should be from total flow rate, input 1, fresh benzene your set point. So the value of this ratio should be your 141.2385 divided by 105.26, 1.341806, 1.341806, and then your FBFC is your cascade. Now after getting all these, we have to initialize it. After initialization you will get the result in all the ratio controller. I have initialized it and my initialization is run as completed. After initialization I have seen that all the data in the ratio controller will be there, so I have to just verify it is correct or not. So for L by F3 mass flow rate is 21,485.3. Here I wait 21,485.3. For C2 we have 10,387.9, 10,387.9, and here is 2385,239. Okay, everything is correct. And we have to check one more thing, that is lag value. Lag value is 2.53733. Okay, here we get 2.53733. Okay, 10.5925, 2.57336. Okay. Okay. Then now we will initialize. We have initialized the all the controller. After initialization and see all the result, and we have seen all the results are correct. If this is your case, then first work is you have to do is take a snapshot and give any value. Snapshot is always necessary. It is necessary because when you run the dynamic simulation and you want to rewind to the initial steady state, you need a step point to where you want to go from the dynamic result to initial steady state. So that's why your snapshot is necessary. After taking a snapshot, save your file, and when you save your file, then go to the dynamic environment. Go to dynamic environment and open some of the controller graphs and do the tuning of all the temperature controller as given for Ziegler-Nicholas tuning, and for pressure you have to do tuning. For temperature controller you have to tune for the Tyrus-Levin, and for pressure controller you have to tune for the Ziegler-Nicholas. C3 condenser. I will show how to tune. I will show only C1 condenser pressure, how to tune for Ziegler-Nicholas or Tyrus-Levin. For pressure we have to tune for the Ziegler-Nicholas. I will show only for the C1 condenser pressure, and after that you have to do it and make a report accordingly to the problem statement. Now run the simulation and see. Wait for some time and see the timing here. If timing goes very fast, that means you have clearly mentioned all the actions and everything, and I will do the tuning of the C1 condenser pressure. So for C1 condenser pressure, go to the tune, click on the tune tab, and then go to the closed loop ATV and start. Wait for some time. When you get approximately sustained oscillation, then finish the test. Sustained oscillation, your process variable is shown by the blue line, so you have to see the sustained oscillation on your blue line, not green one. Green one is your control variable. Wait for at least 1 hour. In 1 hour it will give you a sustained oscillation. If it will not give you a sustained oscillation, then wait for 5 hour. So I will finish my test after 2 hours. So wait till 2 hours. Now my 2 hours finished, and I will finish the test because I have seen that it will give a sustained oscillation. So I will finish my test. After finishing, just pause your dynamic simulation, rewind at your snapshot point, that is 1. I have given the name 1, rewind, and go to the tuning parameter here and open your tuning parameter of C1 condenser pressure and calculate PI controller for Ziegler-Nicholas tuning and calculate. And after calculating, you will see the gain is approximately 119 and integral time is 11. Just update the controller. Since you can see that the gain value is very much high, 119 is very much high, so you can decrease it by divide by 2 and you can give the value of 60 also here, no problem. And then again initialize it, take a snapshot, give a name, go to dynamic, run the simulation. So I will show one more thing here. I will give a disturbance on the fresh ethylene flow rate and see it will for my initial tuning it will controlled or not. So I will give approximately 9 to 10% of disturbance. Let's see, and open one of the temperature controller also, and let's see it will control or not. CSTR TC is controlled. Your FVFC and FPFC controlled. C1 condenser pressure, it will increasing. C2 condenser pressure also increases. C3 condenser pressure also increases. Let's wait for some time. Except for the C2 drum or C2 drum is problem is C2 drum. No, there is not a problem. It is coming back. It seems to be for initial tuning. It will be control. It will control the disturbance. So I will stop here, and I will show one more thing here. In the problem statement, you have asked for to show the graph for the ethyl benzene POT. To do that, you go to the Explorer, go to the flow sheet, and here in flow sheet you have add form. In add form, give a name ethyl benzene EBPOT or EB quality, and plot name. There is no space required, so EBPOT. After getting this tab, you just open this stream, and in that stream you have EB composition 0.999. Just drag here. When you drag it, you have the one more plot of EBPOT, and when I run the simulation, and give disturbance of 5%, you can see POT will be changed. POT will decreases. Nine nine eight nine 53. Here you can see it is decreases as you increase here, as you give the disturbance. Now the video is over. Now you have to complete this dynamic lab as shown in the video, and additionally you have to tuned for Ziegler-Nicholas for all the pressures, and Tyrrell level tuning for all the temperature, and you have to report all the tuning in the report, and along with the some graphs also. Okay, bye.